Chapter 10, pH and acid rain. Recall from Chapter 2 that a proton which has the symbol H+ is a hydrogen atom that is missing its only electron. And because most hydrogen atoms do not contain any neutrons either, the only particle in H+ is a proton. In aqueous solutions, protons do not exist on their own. They are always surrounded by water molecules, just the way all ions in aqueous solutions are surrounded by water molecules. There are two ways to depict a proton in aqueous solutions. First, we can use the symbol for a proton and follow it with abbreviation for aqueous, like the one on the left, H+ followed by AQ in parentheses. In this case, we still refer it as a proton. Alternatively, we can write a symbol that represents the proton combined with a water molecule, like the one on the right, as H3O+. When we write the proton as H3O+, we refer to it as a hydronium ion. We can use the term proton and hydronium ion interchangeably in most circumstances. As we will see, it's sometimes convenient to use one symbol in one situation and the other symbol in another situation. A beaker filled with high purity water contains water molecules, but at any given time, a few of those water molecules are undergoing a chemical reaction known as autoionization. During autoionization, the water molecule splits and produces two ions. H+ ion, also called proton, and OH- ion is known as hydroxide ion. From the Lewis structure of water, there are 8 valent electrons in this molecule. 4 of them are in the bonds, and the other 4 are in 2 non-bonding pairs. When water autoionizes, one of the 2 OH bonds breaks, and both electrons in that bond go to the oxygen. The hydroxide ion that forms includes all 8 electrons and a negative charge. This leaves the proton, which has no electrons and a positive charge. Notice that the autoionization reaction has a double arrow. This double arrow means the reaction goes in both directions at once. We say that the system is at equilibrium when the rates of the two opposing reactions are equal. For the autoionization of water, the system is at equilibrium when the forward reaction, in which water is ionizing to form H+ and OH-, takes place at the same rate as the reverse reaction, in which the two ions, H+ and OH-, come together to form water. At 25 degrees Celsius, 1 liter of pure water contains 1.0 times 10 to the minus 7 moles of H+ and 1.0 times 10 to the minus 7 moles of OH-. We express the concentration of a substance dissolved in something else with molarity, which is the number of moles of a substance in 1 liter of solution. Therefore, we can say that the proton concentration is 1.0 times 10 to the minus 7 molar, and the hydroxide concentration is the same 1.0 times 10 to the minus 7 molar. In 1 liter of pure water, only about 1 in every 550 million molecules autoionizes to form a hydroxide ion and a proton. Thus, pure water is mostly water molecules, but it has a few ions as well. An acid is a substance that increases the concentration of protons in an aqueous solution. Water becomes an acidic solution when an acid is added to it. Because an acid increases the number of H+ ions, 1 liter of an acidic solution contains more than 1.0 times 10 to the minus 7 moles of H+ ions. Acids ionize in water to produce protons. Hydrochloric acid, or HCl, is a gas, and when it is bubbled into water, both the proton and the chloride ion become surrounded by water molecules, as shown in the figure below. Because HCl releases protons into water, we know that it must be an acid. This reaction goes in one direction only, as represented by a single-headed arrow. This means that all of the HCl that goes into the water makes ions. There is no HCl remaining, and no reverse chemical reaction takes place. The term we use to describe this process in which an acid makes ions in water is dissociation. Hydrochloric acid dissociates in water completely. We call it a strong acid. Other acids only partially dissociate in water. We refer to it as a weak acid. In this case, we use double arrow to show that the reaction is at equilibrium. A base is anything that adds hydroxide ions to a solution. It often contains an OH in its formula. Here are some examples of bases: sodium hydroxide, lithium hydroxide, calcium hydroxide, barium hydroxide, and potassium hydroxide. The same theory applies to base, that strong base completely dissociates in water, and weak base only partially dissociate in water. When talking about the concentration of H+ ions in solution, it could be very high or extremely low. Because these concentrations are so important and used so often, many years ago, chemists devised a pH scale to simplify how the numbers are reported. Rather than saying pure water has a proton concentration of 1.0 times 10 to the minus 7 molar, we can simply say pure water has a pH of 7. Typical pH scale goes from 0 to 14, with 7 being neutral. pHs of less than 7 indicate acidity, whereas a pH of greater than 7 indicates a base. Below shows the pH of some common substance. To determine the pH, we take the negative log of the molar concentration of protons in the solution. The brackets around the H+ indicates that we are talking about the molar concentration of protons. For example, suppose we want to know the pH of pure water. We start with the molar concentration of protons in it. Given that is 1.0 times 10 to the minus 7 molar, the pH is calculated as the negative log of 1.0 times 10 to the minus 7 molar. Once you punch this into the calculator, you will get pH equal to 7 for pure water. Pure water is tasteless, neither sour nor bitter. pH 7 defines the neutral pH. Acidic solutions have pH less than 7. Let's take a look at another example. Given a solution with a pH equal to 4.5, what is the concentration of H+ ions in solution? We're going to apply the same formula, but this time we're going to plug in 4.5 into pH. When you solve this, most importantly is to get rid of the log. You're going to use base 10, so that you're going to put 10 to the minus 4.5 exponent to get the concentration of the H+ ion in solution. If we add hydroxide ions to a solution, the pH value increases above 7, and the solution becomes a basic solution. We call anything that adds hydroxide ions to a solution a base. Suppose we make a solution that contains 1.0 times 10 to the minus 2 molar hydroxide ions by adding a base to pure water. If we want to determine the pH of this solution, we start with the OH minus concentration rather than the H+ concentration. We calculate the pOH exactly the same way we did with the pH. The pOH is the negative log of the molar concentration of the hydroxide ion. Then we can plug in figures into the pOH equation exactly the way we did it for pH. To find the pOH of our basic solution, we complete the following calculation. pOH equal to negative log then plug in 1.0 times 10 to the minus 2 molar. That equal to 2 for POH. Because chemists are used to think about pH rather than POH, they use the following relationship to convert back and forth between pH and POH. That is, pH plus POH equal to 14. Knowing this relationship, we can quickly determine the pH of our solution. pH is equal to 14 minus the POH, which is 14 minus 2 equal 12. In our example, the pH changed from 7 in pure water to 12 when the base was added. Bases, by definition, increase the pH by increasing the concentration of hydroxide, and basic solutions have pH values greater than 7. Regardless the solution is acidic or basic, it should be treated with respect because it can cause serious skin burns. In the laboratory, pH can be measured with a device called a pH meter. But before pH meters were widely available, chemists measured pH using an indicator. An indicator is a brightly colored molecule that changes color as the pH of the solution containing it is changed. For example, the indicator phenolphthalein is colorless at pH values below 8.3, but it is bright pink at pH values greater than 8.3, as shown below. Indicators are available for almost any pH range. In fact, a product called a universal indicator is a mixture of several different organic molecules, each one changing color at a different pH. As shown in Figure A, a universal indicator is sensitive enough to allow solutions that differ by 1 pH unit to be distinguished. Figure B illustrates how we can reveal the pH of different household products by adding a few drops of indicator to each one and comparing the colors to the pH values in Figure A. Most natural waters, including lakes, rivers, and oceans, do not have a pH value of 7. They are not chemically neutral. How do natural waters become acidic or basic? The answer to this question is exceedingly complex because many things can affect pH. But one of the most significant factors that determines the pH of a body of water is the air above it. Air is mostly nitrogen and oxygen molecules in addition to small amounts of other naturally occurring gases. Human activities have also added several gases to the mix. Some of these gases form acids when they mix with water, and they are the gases responsible for acidifying rain. Acid rain is the rainfall that has a lower pH than natural and polluted rain. The pH of acid rain is even lower than the pH of clean rain, which is weakly acidic and has a pH of about 5.5 to 6. Acid rain is caused by atmospheric pollution, and it results in harm to the environment. And when the temperature drops below the freezing point of water, acid rain becomes acid snow, which also harms the environment. The Clean Air Act of 1970 charged the Environmental Protection Agency, EPA, with setting limits on the amount of gaseous pollutants that can be released into the air in the United States. These limits are reported in the National Ambient Air Quality Standards, which the EPA updates occasionally to address the new challenges to the environment. The table below lists the new allowable maximum levels of the most insidious air pollutants. There are two concentration units, parts per million ppm and parts per billion ppb. These units are frequently used to express a very small amount of one thing mixed in with something else. For example, if the concentration of ozone in the air is 75 parts per billion, this means that there are 75 ozone molecules per 1 billion air molecules. Ozone is a molecule that naturally exists in Earth's upper atmosphere. It's produced unnaturally when sunlight and smog react with oxygen molecule. Although the natural ozone in the upper atmosphere helps protect us from damaging UV light, this same substance is toxic when formed near Earth's surface and can cause lung disorder in people who breathe it regularly. Another gas listed in the table is carbon monoxide, a potent greenhouse gas. It traps heat in Earth's atmosphere and contributes to the climate change and global warming. These two gases are troublemakers. They are toxic pollutants that are present in the air, especially in urban areas. But neither of these two gases contributes to acid rain. Sulfur compounds are one of the two major sources of acid rain. When sulfur dioxide mixes with oxygen and water in the air, the product is sulfuric acid, H2SO4. In rainwater, as well as the lakes, rivers, and oceans into which it falls, sulfuric acid is a problem. Because it is a strong acid, it completely dissociates in water and releases protons. These protons reduce the pH of the water. Natural unpolluted rain has a pH of about 5.6, but in the US, acid rain typically has a pH of about 4.5. This may not seem like a big difference, but the pH scale is logarithmic. So a shift of 1 pH unit means a 10-fold change in the concentration of protons. Therefore, acid rain with a pH of 4.5 has more than 10 times more protons than clean rain that has a pH of 5.6. The lowest record acid rain was in Wheeling, West Virginia in 1979. The pH was measured at 1.5. It is more acidic than the concentrated lemon juice. At this pH levels, it is not safe to go outdoors when it is raining. The vast majority of sulfur dioxide released into the air comes from one source, coal-burning electrical power plants. The figure to the right lists the sources for electrical energy in the US. These data show that coal generates 3 times as much electricity as more renewable forms of energy do. The reason behind this is simple, that coal is cheap and readily available in the majority of the states in the US. The 2011 EPA guidelines impose stricter limits and require that most existing coal plants restrict what they release into the air as they burn coal. To remove sulfur dioxide from air, coal-burning plants can scrub the flue gases that leave their smokestacks. The term scrub does not mean cleaning with a scrub brush. Rather, it means clean flue gases by removing an undesirable component, in this case, sulfur dioxide. One of the most effective scrub methods is flue gas desulfurization. As previously noted, sulfur dioxide is present in flue gases. It is present because the sulfur contained in the coal forms sulfur dioxide when it is burned in air. In the scrubber, this sulfur dioxide gas comes in contact with jets of a watery limestone slurry, which contains calcium carbonate, CaCO3. These two substances undergo a chemical reaction to form solid calcium sulfate. These calcium sulfates can then be used in making drywall when building houses. The downside is that this reaction also produces a lot of carbon dioxide, a greenhouse gas. Not all coal is the same. Coal plants in the US use 4 types of coal, and they differ in cost per kilogram, the amount of sulfur they contain, and how much energy they produce. Most coal in the US mines is either bituminous or subbituminous, so these two types make up most of the coal we burn. Bituminous coal, which is mined mainly in the Midwest and the eastern United States, is more expensive than other types and contains a lot of sulfur. Subbituminous coal is less harmful because it has a low content of sulfur. It is also very cheap. The graph on the right shows the amount of sulfur dioxide produced by scrubbed and unscrubbed coal for each type of coal in the US. Coal is dirty. Besides contributing to the pollution that causes acid rain, coal releases toxic substances such as mercury into the air and poisons the environment. The biggest problem with coal is that it is not a renewable resource. It is mined once and burned once. Sulfur dioxide emissions have dropped significantly over the years, but most coal produced in plants is still without scrubbers as shown in the picture above. Coal plants without scrubbers accounts for most of the US sulfur dioxide emissions. The circle size relates to the number of tons of sulfur dioxide released by a plant. The larger the circle, the greater the sulfur dioxide emissions. The key for dot colors is shown to the right of the graph. Industrial and agricultural uses of nitrogen disrupt the nitrogen cycle. As illustrated in the figure, nitrogen moves through the air, the ground, and the water. Most nitrogen exists in the air in the form of nitrogen molecules. When this inert nitrogen gas reacts to become part of other substance, we call this process nitrogen fixation. Certain plants and bacteria are specially equipped to fix nitrogen and assimilate it into organic compounds. Lightning strikes can also fix nitrogen. Once it is fixed, the nitrogen that exists in the soil can form different ions, such as ammonium, nitrites, and nitrates. These forms of nitrogen become nutrients for plants. Nitrogen-containing compounds naturally occur in soil, but additional nitrogen is added to the soil in enormous quantities through agricultural activity. The excess nitrogen from fertilizers leaches from the soil and drains into natural waters. In natural waters, extra nitrogen promotes rapid growth of some organisms, such as plankton, and large blooms of these organisms require oxygen to live. When such organisms are present, they quickly consume the available oxygen in water, leave little or no oxygen for other organisms that need it. When a pollutant causes an overgrowth of an organism and oxygen is consequently depleted from natural water, this is called eutrophication. When oxygen levels begin to fall in natural waters, the water first becomes oxygen deficient. As levels continue to drop, the eventual result is formation of a dead zone, an area where life cannot thrive. The photo at right shows the increase in global dead zones from 1969 to 2011. Nitrogen oxides are byproducts of burning gasoline and contribute to acid rain. Recall that air contains 78% nitrogen and 21% oxygen molecules. In a gasoline, nitrogen molecules are brought in from the surrounding air and easily heated over 500 degrees Celsius in the combustion chamber. The nitrogen-nitrogen triple bond breaks and reacts with oxygen molecules to make two different nitrogen oxides, which we describe by writing NOx. When the subscript X is 1, the molecule is NO, nitrogen monoxide. And when the X is 2, the molecule is NO2, nitrogen dioxide. When we want to refer to both of these oxides of nitrogen together, we call them NOx or nitrogen oxides. Nitrogen oxides are gases that form acids when they combine with water. When dissolved in an aqueous medium such as snow or rain, nitrogen oxide molecules form nitric acid, HNO3. Because it is a strong acid, nitric acid completely dissociates to produce protons and nitrate ions. The protons this reaction produces dissolve in rain and snow and acidify them. Catalytic converters are part of the exhaust system in cars. They reduce the emission of harmful gases from cars. The catalysts are typically made with expensive metals of rhodium, platinum, and palladium. Unburned hydrocarbons, nitrogen oxides, and carbon monoxide are all converted to less harmful gases when they flow through a catalytic converter, which contains those metal catalysts. Carbon dioxide, nitrogen molecules, and water are all released at the other end of the converter. The implementation of the catalytic converter has led to the decreased nitrogen oxide emissions over the past 30 years. However, nitrogen oxide emissions have decreased more slowly than sulfur dioxide emissions. Although the amount of nitrogen oxide released per car has decreased significantly, the number of cars has increased, and it will continue to increase. The EPA has released new fuel economy standards. This increased fuel efficiency translates into reduced car emissions, which will mean less nitrogen oxide and presumably less acid rain. Natural waters have a limited tolerance for added acid. A lake that is unaffected by human activities has a pH between 6 and 7. When excessive amounts of acid produced by air pollutants lower the pH, the lake environment begins to change. When pH begins to drop, aquatic plants begin to die, and this adversely affects waterfowl that depend on those plants for food. As pH continues to drop, the bacteria that decompose dead organisms begin to die, leaving a build-up of organic matter. When pH drops below 4.5, no fish can live. The bar graph on the right is prepared by the EPA that shows the pH levels at which different species of aquatic life can survive. Acid rain harms forests as well as bodies of water. pH levels vary across the U.S. Some forests receive more acid rain than others. In areas of heavy industrial activity, where sulfur dioxide is pumped into the air by factories, and areas of high urban density, where cars add nitrogen oxide to the air, the pH of acid rain is lowest. Other areas that are downwind of industrial or urban areas are also affected. This is especially true in the rural areas of the U.S. Northeast. The figure shows a photo of pine trees that have been exposed to the acid rain. Acid rain leaches calcium from tree leaves and from the soil in which the tree grows, and the calcium is lost from the tree. A tree that doesn't get enough calcium gets sick. Sick trees are more susceptible to cold and disease. And there's more. Many soils have aluminum-containing minerals that are naturally present in the soil, but in a healthy ecosystem do not dissolve and release aluminum. However, when the pH drops due to acid rain, the aluminum minerals begin to dissolve and toxic aluminum ions are released into the soil. Aluminum stunts the growth of healthy roots, as shown in the figure to the right. It also reduces the amount of calcium the tree takes in through its roots, and it kills healthy bacteria in the tree. Soils in the Midwestern states of Nebraska and Illinois have soils that are buffered. Those soils naturally contain compounds called buffers that react with excess acid in rain and reduce their effect on the forests grown in those soils. This figure summarizes the sources of acid rain and the effect of acid rain on our environment. Question 1. What is the chemical formula of the hydroxide ion? A. H3O+, B. H+, C. OH-, D. H2O. Please pause your video here. The correct answer is C. OH minus. Choice A, H3O plus is called hydronium ion. B, H plus is a proton. Both of these are for acids. Question 2. What is a strong acid? A. Strong acids partially dissociate and produce a solution with a pH less than 7. B. Strong acids completely dissociate and produce a solution with a pH less than 7. C. Strong acids partially dissociate and produce a solution with a pH greater than 7. D. Strong acids completely dissociate and produce a solution with a pH greater than 7. Please pause your video here. The correct answer is B. Strong acids completely dissociate and produce a solution with a pH less than 7. We know that acid has a pH less than 7 and base has a pH greater than 7. Therefore, we can rule out choice C and choice D. Strong acid that completely dissociate in water, and weak acid only partially dissociate in water. Therefore, choice B is the correct answer. Question 3. What is the pH of this solution? Hydronium concentration equal to 1.0 times 10 to the minus 4 molar. A. pH equal to 1.40. B. pH equal to 0.00040. C. pH equal to 10.00. D. pH equal to 4.00. Please pause your video here. The correct answer is D. pH equal to 4.00. In order to solve this question, you need to use the formula pH is defined as negative log of the concentration of the hydronium ion. Therefore, you just have to plug in the H plus concentration, 1 times 10 to the minus 4. Then you will get pH equal to 4. That's choice D. Question 4. Select the statement that is true. A. A solution is basic if it has a pH of 5.0. B. Solution is acidic if it has a pH of 9.0. C. A solution is acidic if it has a proton concentration of 1.0 times 10 to the minus 2 molar. D. A solution is basic if it has a proton concentration of 1.0 times 10 to the minus 6 molar. Please pause your video here. The correct answer is C. A solution is acidic if it has a proton concentration of 1.0 times 10 to the minus 2. Let's take a look at the choices one by one. A, telling you the pH is equal to 5. So therefore, when pH is equal to 5, this is acidic. Choice B, pH is equal to 9.0. This is basic. Anything greater than 7 is basic, anything less than 7 is acidic. At 7 is pH neutral. Choice C is giving you the concentration of the proton. So therefore, you're going to plug in the formula, pH equal to negative log of the proton concentration. So 1.0 times 10 to the minus 2. You plug this into calculator, this gives you pH equal to 2. So therefore, this is acidic, it's less than 7. Last one, pH equal to negative log of 1.0 times 10 to the minus 6. This will give you 6 pH. So this is also acidic, but the question says this one is basic. That's why D is wrong. Only left you with choice C as a correct answer. Question 5. What is the pH of a 1.0 times 10 to the minus 3 molar solution of a lithium hydroxide? A. pH equal to 3. B. pH equal to 11. C. pH equal to 7. D. pH equal to 17. Please pause your video here. The correct answer is choice B, pH equal to 11. When reading this question, the concentration given here is for hydroxide because the lithium hydroxide is a base. So let me just write it in here. So the concentration of OH minus is 1.0 times 10 to the minus 3. Then we can just simply looking at the choices and then eliminate the wrong answer. Well, choice A, pH is equal to 3, is acidic, but hydroxide is a basic solution. So A is wrong. And then we have pH equal to 7, this is a neutral, it's not basic, so C is out. And then we know that pH scale is from 0 to 14, 17 is out of the range, so D is out. That will only give you choice B for answer. Well, if you want to do this question mathematically, what you're going to do is POH is equal to negative log of concentration of OH minus. And then you plug in the concentration of hydroxide, which is the 1.0 times 10 to the minus 3. So POH is equal to 3 after you punch this whole thing into the calculator. And then we also know that pH plus POH is equal to 14. So you can solve the pH by 14 minus 3 is equal to 11 for the answer. Question 6. What chemical process occurs when metals slowly deteriorate when they are exposed to the environment? A. Corrosion. B. Precipitation. C. Melting. D. Combustion. Please pause your video here. The correct answer is A. Corrosion. Precipitation describes things that are falling, such as rainfall, where ions are falling out of solution and re-entering the solid phase. Melting is a phase change when a solid turns into a liquid. Combustion is a chemical reaction between substances, usually including oxygen and usually accompanied by the generation of heat and light in form of flame. Too much humidity or condensation of water vapor from the environment on metal surfaces are the primary causes of corrosion. It is usually a very slow process. Question 7. What chemical contributes to the formation of acid rain? A. Sodium chloride. B. Sodium hydroxide. C. Carbon dioxide. D. Sulfur dioxide. Please pause your video here. The correct answer is D. Sulfur dioxide, SO2. The common pollutants found in air that causes acid rain are sulfur dioxide and nitrogen dioxide. Question 8. In addition to acid rain, what is another pollutant that is emitted by coal-fired power plants? A. Lead. B. Chromium. C. Mercury. D. Arsenic. Please pause your video here. The correct answer is C. Mercury. Coal is dirty. Besides contributing to the pollution that causes acid rain, coal releases toxic substances such as mercury into the air and poisons the environment. Question 9. How do vehicles reduce about 90% of their nitrogen oxide emissions? A. Low sulfur gasoline. B. Catalytic converters. C. Scrubbers. D. Acid reducers. Please pause your video here. The correct answer is B. Catalytic converters. Catalytic converters are part of the exhaust system in cars. Unburned hydrocarbons, nitrogen oxides, and carbon monoxides are all converted to less harmful gases when they flow through a catalytic converter, which contains metal catalysts. Carbon dioxide, nitrogen molecules, and water are released at the other end of the converter. Question 10. Select the gas that is emitted by burning gasoline that is a precursor to acid rain. A. Nitrogen oxides. B. Nitrite. C. Nitrate. D. Nitric acid. Please pause your video here. The correct answer is A. Nitrogen oxides. Nitrogen oxides are gases that form acids when they combine with water. When dissolved in an aqueous medium, such as snow or rain, nitrogen oxide molecules form nitric acid, HNO3. Because it is a strong acid, nitric acid completely dissociates to produce protons and nitric ions.